Hey Dragon Slayers! Today's video is about fat cell size and its connection to insulin resistance, part 2. Why might fat cells grow in size instead of in number? What makes them turn bad? From what we've learned, there are a couple of known causes. Paradoxically, two distinct fat products can hurt the fat cell's ability to store fat in a healthy way, forcing the fat cells to stop growing in number and to start growing in size instead. Before we look at what these fat molecules do, a brief biochemistry lesson might be helpful. Fatty acid is the technical term for an individual fat molecule. Each molecule consists of a row of carbon atoms with hydrogen atoms linked to them. The number of hydrogens can differ between molecules, which is a sign of whether the fatty acid is saturated, having the maximum number of hydrogens, or unsaturated, having less than the maximum number of hydrogens. The first and likely worst fat molecule that makes fat cells hypertrophic is called 4-hydrononenal. I might be pronouncing that wrong. It's also known as 4-HNE for short. So 4-HNE is a little monster that is born from the unholy union of a polysaturated fat, such as an omega 6 fat, and reactive oxygen molecules, or oxidative stress. Because of the unique structure of the fat, that is, all unsaturated bonds, and the positioning of those bonds, omega 6 fats are very, very easily oxidized. Importantly, linoleic acid, the omega 6 fat of the Western diet, is essentially the main fat in all processed and packaged foods. And, not surprisingly, it has become a significant part of the fat we store in our fat cells, constituting roughly 1/4 of all the fat in our bodies. It's increased almost 150% in the last 50 years. With this in mind, it's easy to see the sequence. Reactive oxygen molecules bump into the highly prevalent stored linoleic acid, creating 4-HNE, which accumulates and disrupts the fat cell's ability to proliferate, forcing it to grow in size rather than grow in number. So the second fat character that disrupts fat cell growth, forcing hypertrophy, is called a ceramide. Ceramide, sorry. It's a 1-phosphate C1P. Whereas 4-HNE is a consequence of oxidative stress, C1P can be considered more of a consequence of inflammation. Through a series of steps, a cell can create C1P from other innocent fats, but the initial steps are turned on by inflammation signals. However, it happens that C1P occurs to a certain point. It flips the same switches as 4-NE, and the cell becomes limited in their ability to multiply, increasing fat cell insulin resistance. But the story isn't over yet. As mentioned earlier, regardless of the mechanism, we know that having more smaller fat cells is better, metabolically speaking, than having fewer larger fat cells. For reasons including lack of insulin response and poor blood flow, the larger, fewer fat cells begin leaking not only fat but also proteins called cytokines and promote inflammation. As the fat cells continue belching these toxic contents into the bloodstream, tissues downstream of the fat cells, including the liver and muscles, are also victims. So, in this fat centric perspective, the fight starts in the fat cells but soon carries over to the liver, muscles, and so many more. So let's take a look at ectopic obesity. Fat should be stored in fat cells. That is the genetic way that it's designed to be. So, this is how our bodies are built. I mean, it makes sense. We certainly do have a limited capacity to store fat elsewhere, but ideally, this is kept at a minimum. When we store too much fat in non fat tissues, it's called ectopic fat. Problems arise, including insulin resistance. A few tissues appear highly relevant to this process, including the liver, pancreas, and muscles. Once they become insulin resistant, the rest of the body starts to feel it. In each of these tissues, there is a reflection of what we see in the sick fat cell. It's storing the wrong kind of fat. Triglycerides appear to be benign even outside of our fat cells. The real problem starts when the fat is converted into ceramides. These mean fats comprise the cell's insulin functions, compromise the cell's insulin functions, whether it be in the liver, the pancreas, or the muscle. That's what I've got for you guys today. Don't forget to like and subscribe because it really helps the channel out. And remember, guys, that together, you and I will slay the dreaded diabetes dragon.